It's 11. Let's get started. So I have posted the schedule sheet for post-test meeting on Blackboard. Again, I usually meet with students after the class, after the test, to talk about how you guys are doing overall in this course. And if you are not doing great in this course, then how can you do better? So please sign up on that sign-up sheet. I was thinking about starting the meeting from today, but I was in hurry this morning, so I forgot to bring your tests to my office. So we'll start the meeting from tomorrow. Okay. So let's continue worksheet 13. So we were working on worksheet 13 last time. So we were talking about work and energy and conservation of energy. So we finished number 4. Now let's look at number 5. Okay. So number 5 is about power. So we talked about work. Work is force times displacement. Okay. And we talked about energy. Energy is the capacity of doing work. And we saw two types of energies. One is kinetic energy, the other one is other one is potential energy, and combined they are called mechanical energy. And today we'll talk about power. Okay, so power is how fast one can do a work. So it's whenever you say fast or slow or something that involves time, we use the term rate. Okay, so rate of doing a work. In layman term, you can say it tells us how fast one can do a work. So faster you do the work, more power you have. Okay. So mathematically, power is work done over how much time you take to do the work. Okay, or you can say P is W over T. The unit of power is watt. Okay, W-A-T-T, watt. Symbol for watt is W. Sometimes it's expressed in kilowatt. If it is a large amount of work, it's kilowatt. And sometimes it's also expressed in horsepower. Okay, or horsepower. So 1 horsepower, HP is horsepower, is equal to 746 watt. Okay. So that's the work and power relationship between work and power. We can also write power in terms of force and speed. So we know the formula for work. Okay. Assume that we are applying force in the same direction as the displacement, just for a simple case. Okay. So displacement is to the right and force is also to the right, then theta would be 0 degrees. So in this case, cosine theta would be 1. Okay. So let's just assume that we are applying the force in the same direction as displacement. Then work would be given by F delta x, okay, over time. So that's the work. Now we can write this as F delta x over t, and this delta x over t, if you remember in the very beginning of this course we talked about this. This is the speed. Okay, speed is delta x over delta t, or instead of delta t you can also write just t, because the starting time is always 0, so instead of writing delta t you can just write t. Okay, so this delta x over delta t can be replaced by v, and that's the power. So there are two ways you can evaluate power, or you can calculate power. One is by using this formula. This is the definition of power, work over time. Or you can also use power is equal to force times speed. Okay? So let's look at number 5 to apply the formulas. A 60 kilogram jogger runs up a long flight of stairs in 4 seconds. The vertical height of the stairs is 4.5 meters. So whenever a person climbs a stairs, so the person is exerting force against his own weight. Okay, so weight is trying to pull it down, but in order to climb, the person has to overcome that weight. So here, the force applied by the person is his own weight. Okay, so force is the weight of the person, or you can write mg. And when we calculate the power or work done by the person, we usually use the vertical height. Okay, not this slanted height, but this vertical height, how high he went from bottom to the top. So that's the distance he covered. So the distance covered is h. That means work done by the person is force times delta x. Okay, so force is w and distance is h. What should I use for w? So let's see. So I'm using the same letter for work and weight. That's the problem in physics. Sometimes we need to use same letter for different things. So let me use this capital letter for work and small letter for work. Okay, this is small case w. So here we want to find the power output. Okay, so power output, power of the jogger is, we have the formula, work over time. We also have this formula. So you need to decide which formula would be useful here. So in the question we don't have the speed given. That means we cannot use this formula. That means we need to use this one. Okay, so work is force times distance. Force in this case is the weight of the body or weight of the person, and h over t. Okay. Weight is mg, h over t. So mass of the person is 60 kilogram. G is 9.8, and height 4.5 meters. And time to get to the top, to that height, is 4 seconds. So do the calculation. That'll give you power in watt. Okay? And to get the power in horsepower, HP, you need to divide this watt by 746. If you divide that by 746, then you get the answer in horsepower. So I have this one 660 watt, and then you divide 660 by 746, what do you get? What's that? How many horsepower is that? 0.29? 0.9? 0.89 or yeah, 0.9 rounding, or if you want, yeah, 8.9. Okay. Now it's also asking for how much energy did the person need to climb the stairs. Okay. So the person does some work in climbing the stairs, and we talked about this last time. So whenever you do work, where does the work go? The work goes in some kind of energy. Okay, what is converted to energy? Or you can also ask, where does the work come from? It comes from the energy of the person. Okay, so that means work and energy are equivalent. They are two sides of a same coin. In order to do work, you need energy, and if you do work, it will be converted to energy. So they are equivalent. So that means you can also write power as energy over time, because work and energy are equivalent again. Okay, so we want to find energy. So energy would be power times time. Power is 660 watt, and time is 4.4 seconds. So you do the multiplication of the two numbers, you get 2600. Energy is measured in joules. Okay, so that's that. Now let's look at number 6. So near the corner of Filbert and Leavenworth Streets in San Francisco, the slope on the Filbert is about 17 degrees. So you have some kind of road that is at 17 degrees angle. 1120 kilogram car climbs this hill. Car, okay, moving up, and the car is moving at a constant speed of 13.9 meters per second. So speed is 13.9 meters per second, and it's doing work against friction and drag force. So there is drag force and friction exerted in the opposite direction. We know that friction and drag force are always opposite to the motion. So the car is moving to the right. That means there must be friction and drag in the opposite direction. So let's write F for friction and drag. Okay, it's combined. So let's just write F. It's 890 Newton. So in order to overcome that friction, the car needs some power. Okay, and the power means it has to do some work for some time. Okay, so without power, it cannot overcome the friction. So we want to find what's that power. Okay, so power is work over time. Work is, so there are two formulas for power. One is this one, and the other one is power is force times speed. So we need to decide which formula would be useful here. Right, so we don't have work, although we can use this step by step, but this would be easier than this one, because we have speed given And this force is, what force would be that? So this is moving at constant speed. At constant speed, so when an object is moving at constant speed, the force in this direction would be same as the force in this direction. Okay, that's for constant speed. So that means in order to move at constant speed, if the friction and the drag is 890 Newton, the car will need to exert the same force in the forward direction. Okay? So this is in dynamic equilibrium. So same force to keep it in constant speed. So that this force would be a combination of force in the left direction. Left direction means, let's consider this to be our axis. Okay, this is negative x, this is positive x. So this force needs to be equal to all the forces that are present on the left side. So we need to decide what are the forces present on the left side. So you guys tell me what forces you have here, so you know how to draw the free body diagram. Yeah, we got the friction force, and what else? Yeah, we have a normal force, so which is this way. Okay, that should be perpendicular to the surface, and there is also weight, which is vertically down. So there are 4 forces acting on the car. But what we need here is all the forces that are on the negative x direction. Okay. So tell me what forces we have on the negative x direction. So to move at a constant speed, the car needs to overcome all the forces pointing to the negative x. So we need to decide the forces pointing along negative x direction. So one is friction. What else? There's not only friction present here. There's one more force pointing to the left. What force is that? This normal is all along y direction. This weight has part pointing in the down direction or y direction and part to the x direction. So yes, so W sine 17 degrees. So there is this component of weight, which is W cosine 17. Okay, this is 17 degrees, so this must also be 17. So and then this part of W is W sine 17. Okay, so these are the 2 forces pointing along the left or negative x direction. So both are negative, or you can just combine the 2. Okay, F plus sine 17. So these are the 2 forces on the negative x direction, and that would be equal to the force that the car exerts. Okay. So now let's find the power. So power is this force F plus, I forgot W here, W sine 17. That's the force. Okay, that's the force. And then speed, 13.9. Okay, so that's from this formula. Okay, so let's plug in the numbers. Friction 890. Work, sorry, not work. Don't be confused with this W. Okay, this is the weight here. We are talking about the x component of the weight. So how do you find weight? Weight, the formula for weight is mg. Okay. Mass of the car 1120 kilogram. G is 9.8. Sine 17, and then that is the force to overcome that's the force the car needs to overcome to run at constant speed, but that's the force, and force times speed gives us the power that we are looking for. So we need to do the calculation. So let's do the calculation and see what you get. That's what we are looking for. Okay, seems like you guys are getting different answers. So what I suggest you to do is, oops, what happened? So do step by step. Okay, so first evaluate this value. So you see what you get. So 1120 times 9.8 times sine 70. Tell me what that number is. Okay. So that's the weight you said?
Yeah, with the sign.
That's this whole thing, right? Not just the weight. And then do the math here. What do you get? 890 plus 3309. This one?
Yeah, I got 3,200.
Instead of 3,209.
Okay. And then now let's do the math, okay? See what you get. So that's, yeah, 56,977. 56,977.1 watt. Okay. Now this is a big number. Like I said before, when you have a big number like that, you can write in terms of kilowatt. Okay, so to write kilo in kilowatt, you divide this by 1,000. So when you divide this by 1,000, you get about 57 kilowatt. Okay, so 1 kilowatt is 1,000 watt. So that's the power. There are two ways to find power. Okay, so that's about work, energy, and power. Now we'll start new chapter. So the new chapter is about momentum. So what is momentum? You hear the word momentum in many different fields, right? In sports, in politics, in economics, everywhere. But what is momentum in physics? So momentum is, what is momentum in like everyday use of the, like in different kinds of like contexts? Like let's say you go and watch football or something. What is momentum in that context? Momentum means something that keeps going, right, without stopping. So same kind of thing here in physics. Okay, so it's a measure of inertia of motion. Okay. So greater the momentum, longer an object continues to be in motion. Okay, so for example, you have a big truck and a small car. Both are moving at same speed. Okay, both are moving at, let's say, 30 miles per hour. Which one do you think will have greater momentum? Big truck. So it's harder to stop big truck. Okay, so the big truck tends to continue moving for longer time. So momentum depends on two things. One is first momentum. We denote momentum by P. Okay? We don't use M for momentum because M is for mass. So we use P. So P depends on mass. Bigger the mass, more is the momentum. Like in football, you have a bigger player, heavier player, and a lighter player. Heavier player has more momentum because it has more mass. So momentum depends on mass. Another thing is, let's say you have two balls of same mass, but one is moving at higher velocity, 60 miles per hour, and the other one is moving at lower velocity, let's say 10 miles per hour. Which one would be harder to stop? You have two objects moving at same speed, or not same, have same mass, but one is moving at higher speed than the other one. Yeah, so it would be difficult to stop the one that moves at higher speed. So momentum also depends on velocity. So momentum depends on mass, heavier the mass, more is the momentum. And it also depends on velocity. Greater the velocity, more is the momentum. Okay? So combinedly, we can say momentum depends on mass and velocity. And turns out that this constant, proportionality constant, is 1 in this case. Okay? So P is m times v. So that's the formula for momentum. Momentum is the product of mass and velocity. So the unit of momentum is the product of mass and velocity. Mass is in kilogram, velocity is in meters per second. So the unit of momentum is kilogram meters per second. Okay. So often in our real life, we want to change momentum of an object. Okay. So let's say an object, let's say 1 kilogram object, let's say football or something. Football may not be 1 kilogram, but just let's say some object is moving at some velocity of 2 meters per second. What's the momentum of this object? The momentum of the object is mass times velocity. Its mass is 1 kilogram. Velocity is 2 meters per second. So the momentum is 2 kilogram meters per second. Okay, that's the momentum. Now, let's say you want to change the momentum of that object. Think conceptually. So how do you change the momentum? Okay, so you have a chair moving at some speed. Okay, so it's moving at some speed. Now you want to change the momentum of the object. So what do you need? You add force, yes. So you need some force. So to change the momentum, let's say you want to change the speed to 3 meters per second. Now the momentum, let's say this is initial momentum, that's the final momentum. So 1 kilogram times 3 meters per second is 3 meters per second, 3 kilogram meters per second. So we want to change from 2 kilogram meter per second to 3 kilogram meter per second. And you guys said that you need some kind of force to do that. Okay. Now, is that only the force that changes the momentum, or there is something else? Acceleration and force are same thing. So when you talk about force, that covers the acceleration. So let's say you have two objects that have same mass. Okay. So I want to change the momentum of the two objects. And we know that I need to apply some force to change the momentum. But I'm going to apply force on one for longer than the other. Okay? I'm going to apply force on the right one a little bit longer, okay, and force on this one a little bit shorter. So I'm applying force for longer time on the right one. So which one has greater change in momentum? The one that gets the force for longer time, right? So the change also depends on time. Okay, there is need of force, but change in momentum also depends on time, how long you apply the force. And when you apply force for some time, when you incorporate force and time in the same quantity, it's called impulse. Okay, so I'm applying force for a certain time. Not just force, but also I'm incorporating the time, how long I apply the force. It's called impulse. Okay. So change in momentum depends on not only force, but it depends on impulse. Okay. Change in momentum depends on impulse, which is the product of force and time. So we can write this equation. When you apply impulse, that changes the momentum. And this is called impulse momentum theorem.
Can you also break down the force, the change in velocity?
Yeah, exactly. Yeah. And that's how you get this equation. So we have this equation, F is equal to ma. So if you break this down, impulse is F times t, change in momentum is final momentum minus initial momentum, and then F is, you take this t on the right side, mvi over t, that's m v final minus v initial over t. This thing is acceleration, that's ma. Okay? That's the Newton's second law. So this is actually the consequence of Newton's second law. Okay? It's not a new thing, but it comes from Newton's second law. So impulse is equal to final momentum minus initial momentum. Okay? This is called impulse momentum theorem. It's a very useful theorem. We'll be applying that for solving many problems. Now, sometimes we may plot a graph of force versus time. Okay? So sometimes I may not be applying same force over the time. So when I'm pushing this, my force may not be exactly same. Sometimes I may be applying more force, sometimes less force, sometimes more force, sometimes less force. So my force may be changing with time. So I may be applying sometimes force, increasing force, sometimes constant force, sometimes decreasing force. Okay, so different kinds of force. So let's say I apply force from 0 time to some time, let's say 6 seconds. So what's the impulse between 0 and 6 seconds? If you are given a graph, okay? If you have a graph of force versus time, then the impulse is the area under the curve. So in this case, my question is, how much impulse did I apply? So that is given by this area under the curve. You find the area, and that will give you the impulse, which is also change in momentum. So if someone asks you, what is the impulse or change in momentum from 0 to 6 seconds, then the change in momentum is 6 seconds. Okay, so this is also the change in momentum. So let's see an example that will make the things more clear. Let's look at worksheet 14. So those who are on Zoom, you can download this from week 12 folder. Okay, so please read the question, number 1. So first one is asking what impulse is imparted by bat on the ball during the hit. Okay, so the context here is a player hits a baseball, and when the player hits the baseball, the player doesn't apply same force throughout the time. So the player exerts the force given by the graph. So initially he exerts higher and higher force, and then as the ball moves forward, then the force decreases. Okay, so that graph tells you how the player is exerting the force. So from that graph, we want to find the impulse. How much impulse is imparted to the bat or to the ball. Okay. So the idea here is the bat exerts impulse on the ball, and from Newton's third law, the ball also imparts impulse on the bat. So they have same reaction, action and reaction impulse exerted on each other. So like I said here, impulse is given by area under the curve on this FT graph. So all you need to do is find the area under this triangle, or area of that triangle. So what's the area of that triangle? Do you guys know what the area of the triangle is? You might have seen this in some math, geometry. This is number 1. So impulse is area under the FT graph. In this case, the area is the area of the triangle. What's the formula for area of a triangle? 1/2? Yeah, base times height. So 1/2 base is 8 milliseconds. So it's not, area is not always spatial area, okay, like a plot of land or something. Area could also be different kind of quantities. Right here we are considering base to be time, okay. So our base here is in time, it's in milliseconds, and here our height is force. So force is height, which is 300 Newton. Okay. Now, in order to express this in Newton second, this is in Newton, this is in second, we want to convert this milli to seconds. So always change milli to seconds, millisecond to second. So 1 millisecond is 1,000th of a second. So you need to divide this by 1,000 to get second. And then we'll have the unit of Newton, which is that, and then this is seconds. So let's figure that out. We can cancel 2 zeros here, 2 zeros here. 5. What is that? It's 4, 2, 5. So 6/5, which is 1.2. Is that right? So the impulse imparted by the bat on the ball is 1.2 Newton second, which is also the impulse imparted by the ball on the bat from Newton's third law. And what is the average force on the ball during 8 millisecond time? Average force is just the highest force here in this case. So usually when you don't know the exact force, you can write this as impulse is equal to average force, F average times time. Okay. And here we are finding average force to be impulse over time. Okay, impulse is 1.2 Newton second, and then time is 8 milliseconds. Okay. So 1.2, 8 millisecond is 0.008. So that will give you the same force, the highest force. Okay, so that's number one. Let's look at number two. It's a similar kind of question. A 2 kilogram object moving to the right with speed of 0.5 meters per second experiences the force shown. What are the object's speed and direction after the force ends?
I got 150 instead of 300.
150?
Yeah.
Okay, so it should be 150 then. Let's see. Yeah, you're right. Okay. Sorry, my mistake. That's 150. Yeah. I got 150. So which is not the maximum force in this case then. I was thinking it would be maximum force, but so basically you find the average force in this way, okay? So impulse is given by average force times time, and then the average force is impulse over time, and you just plug in the numbers. So how do we find the object's speed, final speed? So the idea here is when you apply force or impulse on an object, you change the momentum. Okay, change in momentum means you are changing the speed, because momentum change has mv final minus mv initial, so that means changing momentum means changing speed. So to find the change in speed, you can find the change in momentum. Okay, that will give you the final speed. Okay, so the idea here is we want to use momentum impulse theorem. So use impulse momentum theorem or momentum impulse theorem. So what is the impulse momentum theorem? Impulse momentum theorem is when you apply this impulse is F times t, you change the momentum. Change means final minus initial. Okay, this is the final momentum, that's initial momentum. Okay, that's what we want to use. So plug in the numbers. Force, how much force you're applying. It's given by the graph. You see there, force is constant. You're applying 2 Newton force over the time. 2 Newton. And how long are you applying force? How much, for how long? Half seconds, yeah. So half seconds. And mass is, so we have mass and mass common here, so you can actually write this as m v final minus v initial. So mass is 2 kilogram. Okay, v final is what we need to find, and v initial is the object is initially moving at 5 meters second. So this 2 and 2 cancel. So we have 1 Newton second on the left side. On the right side we have 2 kilogram. V final minus 0.5. So divide both sides by 2. You get 1 over 2. Vf minus 0.5. So 1 over 2 is 0.5. So add 0.5 on both sides, you get 1 here. Okay, so Vf is 1 meters per second. 1 meter per second. Now this is not only the way to solve this problem, okay? This is one way. Another way is by using the Newton's second law. You can use Newton's second law, or you can also use conservation of energy to solve this problem. So there are multiple ways to solve the problem, and we are just looking at one way. Okay, so I think we are out of time. We'll continue this in the next class.